Welcome to the intersection of technology, cybersecurity, and society. Welcome to ITSP Magazine. You're listening to a new episode of Stories from Space podcast, where your host, Matthew Williams, examines the history of human spaceflight, the breakthroughs that revolutionized our understanding of the universe and our place in it, and the brave individuals who work tirelessly to advance the frontiers of our understanding. Knowledge is power, now more than ever.
The authors acknowledge that this podcast was recorded on the traditional, unceded lands of the Lekwungen peoples. Hello, and welcome back to Stories from Space. I'm your host, Matt Williams. And today, I wanted to discuss yet another topic that is very near and dear to my heart. And that is the dream of interstellar travel. Of not just braving the interstellar medium, traveling beyond the sun's heliosphere, and reaching another star system, but of actually setting foot on another planet and building a new life there, possibly terraforming it in the process to make it more suitable for our needs. And of course, why stop there? Why not send missions to all of the nearest stars in our galaxy, planting the seed of human civilization, thus guaranteeing that humanity can survive any cataclysmic events back here in the solar system, and creating endless opportunities for growth? Not just in terms of human populations, but in terms of learning, of exploring, of finding some of the answers to the greatest mysteries of life. Up to and including, are we alone in the universe? This idea and this dream of one day achieving it has been with us for generations. In fact, as long as human beings have known that there were other worlds in the solar system that might be like ours, and that other star systems likely had their own systems of planets. The idea of visiting these places and making contact with new and exotic forms of life has existed. However, it has really only been within the last century, particularly with the dawn of the space race, that the idea became a matter of serious scientific thought and speculation, and even detailed mission planning. Before we get into all that, it should be noted that humanity has already sent 2 spacecraft into the interstellar medium. This would be the Voyager 1 and 2 missions, both of which launched in 1977, explored the outer solar system in the 1970s and 80s, and entered the interstellar medium in 2012 and 2018, respectively. In the not-too-distant future, they'll be joined by 3 more spacecraft, the Pioneer 10 and 11 missions, and the New Horizons probe. What's more, 4 out of 5 of these probes carry with them special messages from Earth. This includes the Pioneer plaques that adorn Pioneer 10 and 11, and the Voyager Golden Records, mounted on the Voyager 1 and 2 spacecraft. The Pioneer plaques are a pair of gold anodized aluminum plates that feature a pictorial message. These plaques, which were the brainchild of famed science communicator Carl Sagan, denude figures of a human male and female, along with several symbols that are designed to provide information about the origin of the spacecraft. This includes which planet in the solar system sent it, a graphic depicting the hyperline transition of hydrogen, the most common element in the universe, and a representation showing the rotational periods and distances of 15 local pulsars and their respective distances from Earth, which astronomers believe advanced civilizations would use as a navigation system. Since the periods of these pulsars will change over time, any advanced civilization that intercepts the probes will be able to determine when it was launched based on these values. Meanwhile, the Voyager Golden Records contain sounds and images selected to portray life on Earth. These phonograph records are contained in a gold anodized case with instructions on the front of how to play them, as well as indications of where they came from. The content of these records were selected by a NASA committee chaired, once again, by Carl Sagan. In addition to being a message for any extraterrestrial civilization that intercepts them, these records also serve as a time capsule in case humanity, in the course of expanding beyond the solar system, should intercept them someday. However, it will be thousands of years before any of these spacecraft reach any of the closest stars to our solar system. The same holds true for any propulsion system we are currently capable of creating, which includes chemical rockets, ion engines, as well as any propulsion system that is realizable using today's technology. As an example, consider the closest star to our solar system, Proxima Centauri. This main sequence red dwarf star is located roughly 4.24 light-years away from Earth. The star is part of a triple star system that includes the Alpha Centauri system, which consists of a main sequence G-type star, similar to our Sun, and a main sequence K-type star, otherwise known as an orange dwarf. Proxima Centauri also contains the closest Earth-like planet to our solar system. This would be Proxima b, the discovery of which was announced in 2016 by the European Southern Observatory. What's more, this star orbits within the habitable zone of its parent star. Since its discovery, multiple studies have been conducted to determine whether or not Proxima Centauri could support life. In addition, multiple proposals have been made for sending robotic spacecraft to explore the planet, its atmosphere, and assess breakthrough starshot, the swarming Proxima Centauri concept, and a few others, all of which call for a light sail or a fleet of light sails, which are similar to solar sails, except that in this case they would be propelled by a series of powerful lasers. These proposals emphasize that this method is the only one within our grasp that could deliver a probe to any neighboring star systems within the current generation's lifetime. However, this concept only works for small, lightweight robotic spacecraft. In order to send a crewed mission, which is to say a spacecraft with passengers, to even the nearest star, would take much longer using conventional methods. So barring any innovations or breakthroughs that could possibly lead to faster-than-light travel, or FTL, we'd be forced to rely on a very limited pool of options. So what are they? As mentioned, conventional methods basically come down to technologies that we currently have or have proven to be effective. The most common of these are chemical rockets, which rely on either solid or liquid propellants to generate thrust. To date, the fastest mission to rely on conventional propellants was the Helios 2 probe, which was launched in 1976 to learn more about the Sun and what drives its contributions to space weather. This mission established the record for highest speed achieved by a spacecraft. Using a gravity assist, this probe was able to reach a top velocity of 250,000 miles. Nevertheless, a probe moving this fast would still take 19,000 years to reach Proxima Centauri. Another option is ionic propulsion and Hall effect thrusters, which are much more fuel efficient but achieve maximum velocity very slowly. To give you an example, NASA's Deep Space One mission, which rendezvoused with an asteroid and comet in 1998, relied on a xenon-powered ion drive that managed to achieve a maximum velocity of 56,000 kilometers an hour, or 35,000 miles, which took 20 months of constant acceleration to achieve. At this velocity, it would take a spacecraft 81,000 years to travel to Proxima Centauri. But again, this involved robotic spacecraft. In terms of crewed missions, we should consider the Apollo 10 spacecraft, which holds the record for the high speed attained by a crewed vehicle. In 1969, it flew to the moon without landing, achieved a maximum velocity of 39,888 kilometers an hour, 24,791 miles, and was able to make it to the moon in just under 2 days and 4 hours. To get to Proxima Centauri, however, the Apollo 10 spacecraft would take roughly 114,800 years. So basically, conventional methods are completely impractical when it comes to interstellar travel of any kind. There are, however, a few options for building spacecraft that would utilize proven technology that we simply haven't built yet. A good example of this is nuclear propulsion, which NASA and other space agencies are currently researching for the sake of conducting long-duration missions to Mars and other locations in the solar system. This technology not only offers a high level of thrust, but also fuel efficiency, energy density, and relies on proven technology. For example, NASA developed a nuclear engine concept during the 1960s and 70s, known as the Nuclear Engine for Rocket Vehicle Application, or NERVA. The Soviets experimented with similar technology. In addition, A number of more advanced and efficient concepts have been proposed, which could also be realized in the near future. To break it down, nuclear propulsion comes in two main forms: nuclear thermal propulsion, or NTP, and nuclear electric propulsion, or NEP. In the case of NTP, a nuclear reactor is used to heat liquid hydrogen propellant, which turns it into an ionized gas, or plasma, which is then channeled through nozzles to generate thrust. This type of nuclear engine produces significant acceleration, or delta V, but is less efficient than its counterpart. In the case of NEP, a nuclear reactor converts heat into electrical energy, which in turn powers an ion engine. When these two methods are combined to create a bimodal nuclear spacecraft, the advantages are not only high acceleration at the beginning of a journey, but also consistent acceleration throughout. According to current estimates, the most sophisticated nuclear concept would be able to produce enough thrust to reduce travel times to Mars to just 90 days. When adjusted for a one-way journey to Proxima Centauri, a nuclear propulsion system would take about 1,000 years to reach its destination. Next up, we have a very time-honored concept known as nuclear pulse propulsion, or NPP. This concept was originally proposed in 1946 by Stanislaw Ulam, a Polish-American mathematician who participated in the Manhattan Project. In 1947, he and American physicist Frederick Raines performed the preliminary calculations for a large spacecraft equipped with hundreds or even thousands of nuclear devices, which would be released one at a time in the ship's wake and then detonated. The shockwave would then strike the rear of a ship, where a large push plate would convert the force into forward momentum. In 1947, Ulam and American physicist Frederick Raines performed the preliminary calculations on how long it would take such a spacecraft to reach the nearest stars. Between 1958 and 1963, Ted Taylor of General Atomics and physicist Freeman Dyson, for whom the Dyson sphere is named, came together to spearhead a project known as Project Orion. This project aimed to harness the power of thermonuclear devices to generate high velocities that be capable of reaching Proxima Centauri in just under 20 years. Unfortunately, according to Dyson's most conservative estimates, the cost of building such a spacecraft in 1968 dollars was $367 billion. Adjusted for inflation, that's roughly $3.125 trillion. To put that in perspective, was just over $100 trillion. To put that in perspective, the annual revenue for the United States government in 2022 was $4.92 trillion. There's also the problem of the radiation and nuclear waste the spacecraft would leave in its wake. In fact, it was the passing of the Partial Test Ban Treaty in 1963 that led to the project's cancellation. This treaty banned the testing of nuclear devices in space in order to limit the amount of radiation humanity was contributing to Earth's upper atmosphere. Next up, we have the concept for fusion rocket. And much like nuclear thermal and nuclear electric propulsion, this concept involves rockets that rely on nuclear power, but with the twist of it being thermonuclear reactions rather than fission reactions that generate the thrust. In this case, the concept calls for pellets of deuterium or helium-3 being compressed inside a reaction chamber by electron beams to the point where a fusion reaction occurs. This creates a high-energy plasma that would then be focused through magnetic nozzles to generate thrust. And for fans of The Expanse, there's actually a very nice scene in one of the episodes where they illustrate what the interior of a reaction chamber looks like, and it shows the deuterium pellets being injected and eventually being fused by lasers. And much like your nuclear rockets that rely on fission reactions, this concept has the advantage of fuel efficiency, high acceleration, high thrust, and according to some estimates, velocities of up to 10,600 kilometers per second can be achieved, or 38 million kilometers per hour. And that works out to 23.7 million miles per hour, which puts it in the realm of relativistic speeds, a fraction of the speed of light. In addition, the technology is validated. It's been tested, and this has led to multiple variants being proposed over the years. And this includes the feasibility study conducted by the British Interplanetary Society between 1973 and 78, which is named Project Daedalus. And this concept called for a two-stage uncrewed spacecraft that could be realized using then current technology. And according to their estimates, a ship of this type would be able to make the trip to Bernard's star, located roughly 6 light years away, within a single human lifetime, roughly 50 years. And adjusted for Proxima Centauri, it would be able to make the trip in 36 years. And for those who aren't familiar with the concept, I've been sure to include some graphics, some images there as part of the episode data. And you'll recognize this one as the massive ship with all these huge fuel tanks arranged in 2 rows, standing next to a Saturn V rocket and completely dwarfing it. And according to the plan for this ship, the larger stage would operate for roughly 2 years before it exhausted its fuel supply, and in the process would accelerate the spacecraft up to 7.1% the speed of light. And the first stage would then be jettisoned, and the smaller second stage would accelerate the spacecraft further, up to 12% the speed of light, over the course of another 2 years. Of course, this concept has several obvious drawbacks, not the least of which is the sheer cost of building it. From its size alone, one can estimate that it would be punitive. And to put that in perspective, the SpaceX Starship, currently the largest and heaviest and most powerful launch system in the world, has a mass of 4,536 metric tons when fully fueled, or roughly 5,000 short tons. So the cost of manufacturing and launching such a ship would be beyond anything we can currently fathom. And of course, there's the other stumbling block, which is the scarcity of helium-3, which is very rare on Earth. So this would mean that it would have to be harvested from somewhere else in the solar system, most likely the gas giants. And last but not least, the fusion reaction that drives the spacecraft would need to produce far more energy than what is used to trigger the initial reaction. And on Earth, using tokamak reactors and experiments involving magnetic confinement fusion, scientists have managed to surpass the break-even point and have gotten to the point where they're generating more energy from the reaction than what is needed to initiate it. Unfortunately, they are a long way away from producing anything near to what this spacecraft design would need. However, undeterred, a new organization, Icarus Interstellar, adopted the concept in 2009, and this organization, made up of volunteer citizen scientists, former NASA and ESA workers, they've been working to realize a smaller, more cost-effective version of it. And even though their idea was significantly scaled down and much cheaper in terms of projected costs, there's still the problem of helium-3 scarcity and the problems of producing enough reaction energy, and the cost issue, while less, is still very punitive. And next, we have a very interesting concept that is similar, and for which multiple designs have been proposed, and it's known as a fusion ramjet. And this spacecraft would rely on the same fusion reactions in order to generate thrust, but has the added bonus of not having to bring its propellant with it. And in all cases, when it comes to spacecraft, propellant is the single greatest source of mass. So over the years, many concepts have been proposed where spacecraft could harvest their propellant or just generate propulsion directly from the interstellar medium or from solar wind, aka solar sails. And if you're looking at the images provided in the episode data, this would be the one that looks like a giant blunderbuss or trumpet. And the original concept for a buzzard ramjet was proposed by Robert W. Buzzard in 1960, hence the name. And this, as with similar concepts, because others have been proposed since his time, they all involve this large funnel at the front, which would generate magnetic fields in order to funnel deuterium or helium-3 into tighter and tighter space inside the ship. And with the help of magnetic fields in a reaction chamber, fusion reactions would occur, and that energy would then be channeled through nozzles with the help of more electromagnetic fields to generate propulsion. Now, the chief advantage of this system is, obviously, it doesn't need to bring along its propellant, thus leading to a ship of significantly less mass, And at the time of writing, Robert Buzzard was also encouraged by the fact that hydrogen constitutes over 90% of the interstellar medium, is the most common element in the universe. So on paper, this would seem like a very elegant solution. However, it also has many drawbacks, which once again include cost. While cheaper than building a fusion rocket a la Daedalus or Icarus, it would still cost a tremendous amount of money to build, far beyond anything that we can currently mobilize or imagine. But there are also issues that have to do with the nature of the interstellar medium. Basically, since Buzzard's time in 1960, our knowledge of the interstellar medium has grown considerably, and investigations of the regions surrounding the solar system, it's indicated that this region has a much lower density than previously thought. And so, as a result, the amount of propellant it could actually harness would be significantly less too, thus throwing off the calculations. And furthermore, recent research has suggested that in order for this concept to be feasible, the magnetic field generated by the RAM scoop would have to be enormous. And this includes calculations done in 2021 by Peter Schatz-Schneider and Albert A. Jackson, who indicated that the magnetic field would need to be 150 kilometers in length, or 93 miles, and 4,000 kilometers, 2,485 miles in diameter. And that's what would be needed in the interstellar medium as we know today in order to funnel enough fuel to generate thrust. In addition, multiple studies have been conducted that confirm that drag would be the greatest impediment to acceleration. One of the beauties of this idea is that as you scoop up fuel from the interstellar medium, you accelerate, thus increasing the amount of fuel you're able to scoop up and thus accelerating more. So you're able to gradually build speed over time to the point where you could reach a high percentage of the speed of light. And this idea was featured in Tau Zero, a very seminal science fiction book by Paul Anderson. And that was the first instance of it being written of fiction. However, research has shown that there's a drawback to this, that the very thing that's accelerating you is also slowing you down. Now, in terms of going big, that is to say building very large spacecraft, but also ensuring that this is a crewed mission, because many of the proposals mentioned already called for uncrewed explorer craft, but given their size, could probably be equipped with crew quarters as well. However, this particular concept calls for a very large crew making the journey. That is the concept of a generation ship. And whereas all of the other concepts call for going faster, creating a ship that could reach a nearby star system in a realistic amount of time, a generation ship accepts the notion that such advanced propulsion would take a very long time to realize, or it would take multiple innovations and significant growth before anything of that nature would be considered realizable. And in the meantime suggests building an equally large spacecraft that would be able to accommodate a crew of a few hundred or a few thousand over the course of multiple generations. So basically, don't aim to go fast, except that you're going to be going slow and prepare for the long haul. Now, the concept has been explored extensively in science fiction, but as a matter of scientific proposals, the first recorded example comes from Robert H. Goddard, considered one of the forefathers of modern rocketry, and for whom NASA's Goddard Space Flight Center is named. And it was an essay released in 1918 called The Ultimate Migration, where he described an interstellar arc of cryogenically frozen passengers leaving the solar system after the sun reached the end of its life cycle. And according to Goddard, atomic energy could be used to power the spacecraft should that be realized, which at the time it had not. It would be several more decades. However, he also said that a combination of hydrogen and oxygen could be used for propellant and that the ship itself could be powered by solar energy. And according to his calculations, this would be enough for the ship to accelerate to a maximum velocity of 57,936 kilometers an hour, or 36,000 miles per hour. And the concept also envisioned that the crew would be kept in stasis, while a pilot would be awakened at certain intervals in order to steer the ship and make any course corrections. And as he wrote, the spacecraft would take perhaps 10,000 years for a passage to the nearest star and 1 million years for great distances or for other stellar systems. And this was followed by a similar concept proposed by Konstantin Tsiolkovsky, also hailed as one of the fathers of modern rocketry, who wrote of a Noah's Ark in an essay published in 1928 titled The Future of Earth and Mankind. Now, in Tsiolkovsky's version, the spacecraft would be self-sufficient and the crews would be awake for the journey, which would take thousands of years. And in 1964, Dr. Robert Enzmann proposed the most detailed concept for a generation ship to date, known as an enzyme starship. And in his proposal, fusion reactions would be harnessed, which would consist of deuterium pellets being fused by electron beams, and the ship itself would measure 600 kilometers in length and consist of a large sphere at the front of it, which would house the propellant and also the bridge section, and with the engine and other sections extending far to the rear. And the spacecraft would measure 600 meters in length, or 2,000 feet, and support an initial crew of 200 people, but with room for expansion because, of course, many would be born along the way. Now, of course, such a concept is filled with challenges, all of which would have to be thoroughly researched and addressed in advance. And interestingly, a series of studies released between 2017 and 2019 did this very thing. And the studies were led by Dr. Frederick Marin of the Astronomical Observatory of Strasbourg, using numerical software called Heritage, which Dr. Marin developed himself with his colleagues. And the first two studies, he and his colleagues conducted simulations that showed that a minimum crew of 98 and a maximum of 500 would be needed, along with a cryogenic bank of sperm, eggs, and embryos in order to ensure enough genetic diversity and good health upon arrival. And in the third study, Dr. Marin and a separate group of colleagues, they calculated how much artificial land would be needed for growing food, and determined that this space would need to measure 320 by 224 meters, or 1,050 feet by 735, containing 450 square meters, or 4,850 square feet, of arable land would be needed to grow enough food. And coincidentally, the very first design competition for a generation ship was launched on November 1st of this year, known as Project Hyperion. And the competition is sponsored by the Initiative for Interstellar Studies and includes such notable scientists as Andreas Hein, who's the Associate Professor of Aerospace Engineering at the University of Luxembourg and Chief Scientist at the Interdisciplinary Center for Security, Reliability, and Trust. And he was joined by an organization team. It included many highly respected artists, architects, engineers, anthropologists, landscape architects, and designers, thus representing everything that would need to go into the detailed planning of a generation ship. And the rules of this competition indicate that people will need to design a ship that will accommodate a crew of 1,000 people, plus or minus 500 throughout the trip, and that the duration would be 250 years. And as I said, this is the first competition of its kind and is based on research that, unlike the majority of studies regarding interstellar space travel, focuses on a concept that ensures crew safety and crew health over the long term rather than speed and getting there sooner. Unfortunately, like all the other concepts presented, the generation ship has a number of obvious drawbacks. It would be prohibitively expensive to build, given its size. It would also be very challenging to see to the needs of a crew that numbers in the hundreds or over 1,000. And that, of course, extends beyond simply food and water, which would require a bioregenerative environment. So basically, an Earth-like biome would need to be created inside the ship. And this would not only be necessary for maintaining the supply of food, water, and breathable air, but the psychological health of the crew. And of course, the concept also suffers from one invariable flaw, which is that in the time it takes for this ship to reach its destination, centuries or longer, Faster means of propulsion will likely have been invented. Technological advances will be made that would make such a ship obsolete long before it reaches its destination. But of course, this is a problem for virtually all interstellar concepts, including the theoretical ones. So when it comes to concepts that are realizable today, using today's technology, that have any chance of reaching the nearest star systems in a realistic amount of time, there really only is one concept available. And as mentioned already, this would consist of a light sail and a gram-scale spacecraft or nanocraft, basically all of the instruments placed on a chip, which is then accelerated to relativistic speeds by a laser array. Now, this concept was originally proposed by Robert Forward, physicist at the Hughes Aircraft Research Laboratories in 1984. And the benefits of this concept is, once again, it doesn't require any propellant, which drastically reduces the mass of the spacecraft. And also the fact that the laser energy does not dissipate with distance nearly as much as solar radiation does, as with a solar sail. This gives the light sail the ability to accelerate over very long distances. And in 1999, Jeffrey A. Landis of the NASA Institute of Advanced Concepts, he conducted a Phase 1 concept study on the possibility of propelling a light sail with a laser array. And his concept consisted of a light sail composed of dielectric thin films that could be accelerated up to 30,000 kilometers per second, or 10% the speed of light. And as he argued, the spacecraft would be ideal for, quote, fast transit missions to the outer planets, Kuiper and Oort cloud missions, and interstellar precursor missions. By his own velocity estimates, this mission could reach Proxima Centauri in the space of about 43 years. And in 2000, a similar proposal was made by Robert Frisby, who was a director of advanced propulsion concepts at NASA JPL. And in his version, the light sail would measure 320 kilometers in diameter, or 200 miles, and could be accelerated to as fast as 35% the speed of light, which would cut the trip down to 12 years. He also estimated that a sail measuring 965 kilometers, or 600 miles in diameter, could go even faster. At roughly 47% the speed of light, it would be able to make the journey in just under 9 years. But of course, that would require tremendous amounts of power. According to Frisby's own estimates, 17,000 terawatts. And that's close to what the entire world currently consumes in a single day. But in recent years, the concept has been updated with new variants proposed, the most notable of which is the Breakthrough Starshot concept that was proposed by the Breakthrough Initiatives in April 2016, founded by Russian billionaire Yuri Milner. Once again, the concept was all about sending a mission that could reach the nearest star system in our lifetimes. And several leading scientists were part of this project, including Professor Loeb of Harvard University and Professor Philip Lubin of UC Santa Barbara, who's done extensive work into directed energy concepts, including a NASA mission known as Starlight, which is very similar to Starshot, and the development of wafercraft. In addition, his laboratory, the UCSB Experimental Cosmology Group, they were also looking into lasers as a form of planetary defense for deflecting asteroids. And this concept that they proposed leverages a lot of advancements made in the field of miniaturization, so that this small spacecraft, known as a star chip, be about the size of a smartphone, would be studded with sensors, guidance and navigation systems, and even tiny little electron thrusters. And by their own estimates, this spacecraft, when powered by a 100 gigawatt array, would be able to reach velocities of about 60,000 kilometers a second, or 37,280 miles per second, or 20% the speed of light. And at that speed, it would be able to make the journey to Proxima Centauri in 20 years. Now, this concept grew from a mission study known as Project Dragonfly, which was hosted by the Initiative for Interstellar Studies, or I4IS, in 2013. And both Starshot and another Dragonfly concept were the two top designs. Now, in recent years, Starshot has sort of quieted down as the breakthrough initiatives have come to focus on other initiatives, especially Breakthrough Listen, the largest, most sophisticated SETI project ever mounted. However, other proposals have emerged to sort of fill the vacuum. And again, most notable among them is the swarming Proxima Centauri concept, proposed by Marshall Eubanks, a former NASA scientist and the current chief scientist at Space Initiatives, Inc. And this concept was one of NASA's Phase 1 selections. And interestingly, this concept was selected for Phase 1 development as part of the 2024 NASA Innovative Advanced Concepts Program. And the basic idea is to create a swarm of small, very lightweight disks with reflective material that would again use a 100 gigawatt array to boost them to relativistic speeds, and they would rely on swarm intelligence and autonomous systems in order to maintain contact with each other, make course corrections, and to send high bandwidth communications back to Earth. And as I said, this concept is right now the only feasible means of sending a spacecraft to Proxima Centauri or any other nearby stars. But of course, this one concept is uncrewed. So as it stands, the dream of sending human beings to the nearest star systems, the nearest planets, and setting up shop on them, that is something that is destined to remain a dream. For how long, we don't know. So far, we've discussed the ones that are feasible using today's technology or with advances made in the near future involving technologies that are known to work. In order to do this subject justice, we also need to talk about the theoretical approaches that are not yet possible and probably won't be for some time. However, given the richness of this topic, that's going to have to wait for our second installment coming soon. So stay tuned for part 2 of our look at interstellar travel concepts, where we will take a look at antimatter propulsion, the Alcubierre warp drive, possibility of wormholes, and the concept of black hole propulsion. Also, stay tuned for upcoming episodes where we'll take a look at what the James Webb Space Telescope has revealed about our universe so far, the ongoing question of whether or not rocky planets orbiting red dwarf suns are habitable, as well as episodes that look at other famous and historic missions like the Pioneer probes, and Kessler syndrome and the growing problem of space junk. In the meantime, thank you for listening. I'm Matt Williams, and this has been Stories from Space.
We hope you enjoyed this episode of Stories from Space podcast with Matthew Williams. If you learned something new and this podcast made you think, then share itspmagazine.com with your friends, family, and colleagues. If you represent a company and wish to associate your brand with our conversations, sponsor one or more of our podcast channels. We hope you will come back for more stories and follow us on our journey. You can always find us at the intersection of technology, cybersecurity, and society.